just a sec.
Okay.
Okay.
So please go ahead.
Yeah.
Thank you very much.
Hi everyone, I will talk about statically and dynamically delayed sampling for type probabilistic programming languages, and this is a collaborative work with Daniel Lundén, Viktor Senderov, and David Broman. So probabilistic programming languages focuses on inference, and then a definition for inference is what conclusion we reach after observing an evidence. And let's consider we have like a coin, and then we ask ourselves, is this a fair coin? One way of answering this is like we flip the coin 100 times, and then 83 times we observe heads. A frequentist approach would only consider this likelihood or the observation, and then might say that, okay, then the probability is the ratio, so it's 0.83. But a Bayesian approach, which most probabilistic programming languages focuses on, take the Bayesian approach and then say that, okay, do we have a prior belief? Do we believe that this coin is fair? Then it takes that into account, and then on top of this likelihood, it also includes the prior to calculate the posterior, which is the probability of parameters, or in this case, the probability of heads given data. So what can you do in a probabilistic programming languages? We can embed this model, which consists of our observations and then the prior knowledge we have about can be on coins, but of course in real world they are more complicated models, like can be biological models like phylogeny, evolutionary biology. And then after writing our model, the inference algorithm in probabilistic programming language takes that model and then just generates the posterior, which we are looking for, the answer. And then here, we kind of see that the posterior is shifted toward right, which means the probability of head is higher, which is expected after observing those many heads. And we can divide the probabilistic programming languages into three based on their inference methods, and the first set of methods is Monte Carlo methods. And then in this work, specifically, we focus on making CorePPL, which based on this like sampling, approximate sampling method, and I will explain it in later slides. And then the second set is variational inference. These approaches take the inference as an optimization problem. And then the third one is exact inference, so they directly try to solve that formula, as the name suggests. And I mean, on an ideal world, we would like to, on all models, we would like to use exact inference because that gives an exact solution, so it's more accurate. But on a real world, that doesn't happen because, like in this formula, the denominator consists of a numerical integration. And then the problem is for high-dimensional models, and for most real-world models, this is intractable to calculate if we are using an exact approach. So here, we need to utilize these approximate inference methods, either Monte Carlo or variational inference, so that we can like apply the sampling on more or many real-world models. But in our work, we want to combine the benefits of these two worlds so that we have like high accuracy, but still we can apply this on real-world models. So one way of applying these exact inference techniques in approximate inference algorithm is utilizing the conjugate prior relations within a model. And what are those, like for example, we have this on the top. We have like the somehow notation of this coin example that where we sample the theta is sampling from like the probability of heads, and then we observe our like we toss the coin several times and embed our observations, and the question is like what is the posterior of theta after observing these. So the top model is what normally a user would write it, and then down below, we utilize the exact inference techniques so that the posteriors has a closed form solution. These two models converge to the same posterior, so they give the same solution, but the model on the top requires 1 million steps on like a normal or a naive Monte Carlo method, and then the one below requires only one step. So one key thing about probabilistic programming languages is they try to provide modularity between the inference and then writing the model. And key thing in here is, how the model is written affects the inference a lot, the efficiency of it. So can we somehow automate this process so that the user doesn't have to changing the model? One way of doing this is delayed sampling. It's a runtime approach to utilize the conjugate prior relations. But one problem with a runtime approach is, of course, it adds a runtime overhead. And then our question is, can we solve this? Can we make it more efficient? So before answering that question, I want to give a bit more background information because I'm using these languages or the concepts in my approach. So CorePPL is a statically typed universal probabilistic programming language. And here, statically typed means just types are known at compile time. And then the universal means it is expressive enough to represent any probability model. And then here in CorePPL, this is like on the left-hand side code is some like the coin example written in CorePPL. It has some simple construct. I think it exists on all probabilistic programming languages. One being, or with different maybe terms, but assume here provides sampling from a distribution, in this case from beta distribution, so we sample from a beta distribution, and then here, this actually corresponds to the prior in Bayesian formula. And next, we have the updating the likelihood, and then this corresponds to exactly the likelihood in the Bayesian formula. So in CorePPL, we just write our model defined with prior and the likelihood, and then the inference part, and in CorePPL, it is Monte Carlo methods, just gives us the posterior at the end. So these conjugate prior relations, as I said, normally calculating the denominator requires a numerical integration. However, if there are like special relations between the likelihood and the prior, then we can find exact solutions for the posterior or closed form solutions. And for example, in this coin example, there is a conjugate prior relation between beta and Bernoulli, so we can directly give the result for posterior by just using a simple addition operation, and for marginalized likelihood, which is the denominator as well. But the question is, we are talking here about universal probabilistic programming languages, so it might have complicated dependencies, it might have function applications, and then like iterations or recursion. So how do we solve this? So delayed sampling solves this problem by utilizing the relations at a runtime, and then it maintains a graph to construct the random variables from the runtime by following the program flow. But the problem is it's a runtime approach. So then our first kind of research question is how do we reduce runtime overhead? And the simple answer is why not try this at compile time? And then the second one is the idea of delayed sampling is, if possible, we don't sample from it. It delays the sampling, but this means that we don't have the exact value for something, so it is not sampled yet. How do we then handle the type of that variable in a statically typed system? So what we are doing is we can divide the related work into two. One is runtime approaches that I'm talking, and then our approach falls into compile time approaches. And there are some compile time approaches that are trying to utilize that, but they either rely on some computer algebra or specific to an inference algorithm, or work on a simpler PPL, for example, the only one that have a Bayesian framework. So our aim is here that we want to provide the modularity even between inference and then the optimization algorithm, so the inference doesn't have to change its method for our optimization. And then the second one is it works on universal PPLs, and then the third one is we reduce the runtime overhead by doing this at compile time. So our approach, this is the pipeline for it, but then it's simply just the purpose is increasing given a probabilistic program, at the end we have a transform program, and the difference is now the inference accuracy is increased if we run the inference on these transformed probabilistic programs. So the original delay sampling algorithm, the dynamic one, works on graphs. But the question is, how do we represent the compile time structures in a graph? Because if we do this in a graph, then it will provide some generalizability. And for that, we define these programmatic Bayesian networks that I will give more details on. And the second thing is, the first part of this is just generating from the program and using the AST tree, generating, or abstract syntax, generating these graphs. And then the second one, after the graph is generating, this second step takes the generated graph and then utilizes the conjugate prior relations between them, and then we get a transformed PBN. So the third one is the last step. We wanted a modularity between the inference and then the optimization method. So in the last stage, we are just taking this transformed program and then turn it into probabilistic program again. Just to give an example, in the left-hand side, we have the Mike and CorePPL program, the first step, and then we generate a graph out of it. I will detail this a bit more, but then using the conjugate prior relations, we transform this graph. So this only happens now, we don't really care about the code, but only on the graph. And the final step is regenerating the code from that. So what is the difference between Bayesian networks and its programmatic Bayesian networks? So let's take this simple example. On the first 3 lines, or the first 2 lines, we have 2 random variables, and then we create a list from them. In a normal Bayesian network, I mean, there is no representation of creating a list. You just have 2 random variables. But then we need these information to make the transforms happen. So in our representation, now we have a list node. And at line 4, we have a stochastic random variable that's either 0 or 1, and then at line 5, we try to get an item from that list based on a stochastic index. Again, this is not obvious in a Bayesian network. There is no selection process exactly. So, but our programmatic Bayesian network, we create these nodes that we call multiplexer nodes to select an item from a list. And then finally, we connect the observed, and finally we have observed random variables at the end, and we see that now it depends on the output from the selection, not all of these random variables directly. So with Bayesian networks, we lose actually information, but then with our representation, we gain that information. And further, since we are doing this at compile time, we don't know how to, if there's a function application, it's not obvious how to represent that in a Bayesian network. So we have these code blocks that are not part of the optimization, but we use them to represent these code structures that are not encodable by a Bayesian network. And then the third one is, this is for increased expressibility of our model or of our optimization method, that we also include the plate notation, and then this is very much used in topic modeling. So what is this conjugate prior transformer step? Okay, now we have, let's say we have a graph. So the aim in here is we wanna locally find exact solutions for the relations between random variables. So we want to derive the posterior distribution, and in our, again, toy example, it is the probability of heads. And then for that, we basically do this conditioning step, and then the next is we also want to calculate the marginalized log likelihood to update this observed statement correctly, so it is the denominator. So it's called marginalization. And then using these two operations, in paper you can find like a more detailed, because since it's static time, the interactions between different nodes requires different operations. But for this simple model, for example, first we are trying to marginalize our observation, so it's not going to depend on the node A. And then the second, and that reduces the variance. And then the second one is calculating the posterior for A, which is the conditioning. So then after this one, we have the transformed graph. Then the only thing we require to do is we sort this graph, topologically sort the graph, and then just for each node corresponds to a line or lines in the program. So I will not go into details of this, but we can also handle lists and plates by considering the different interaction between the nodes. And you can find the more like details and the explanations in the paper for that. And then the second contribution of this paper is actually implementing dynamically delayed sampling in a statically typed language. And the problem with this is, let's say we have this example that first we sample from a Gaussian distribution and then like bind it to a variable A. Now A should be a float because like it's going to return a value, and then that value is from a Gaussian distribution. And then the second thing is we have a function that we call fun that takes two arguments, x and o, which first one is the distribution or the value that we sampled from, and then the second one is going to be the observation, and then it just updates the likelihood with observe keyword. Here the important thing is normally distributions expect a value like a float or an integer in a normal PPL that's not designed for delayed sampling. And then here we have some function application, and for applying we give arguments A and an observation, and then on line 4 we just give a float, two float values, and this works perfectly if you don't have delayed sampling. But what happens if you have delayed sampling is, let's say we are delaying the sampling of A. Now A cannot be a float because it's not sampled. But first, fun requires a float, and then second is actually there's a kind of a type complete because we have different types for the same parameter. And how do we solve this is we introduce a user annotated system so that the user gonna use and delayed keywords or the constructs to mark the places that should be delayed. So in this case, it says A should be delayed, and then we are specifically using this delayed keyword because the distributions expect a float value. And then the delayed keyword just ensures they get a float value or an integer value. Here, there is one caveat, is that like we sacrifice from automation for more expressiveness and accuracy. This may sound a bit bad, but also this gives more control to the user, because normally without these delay keywords it would have automatically done it, but the user wouldn't have any knowledge on what was going on in the background, and sometimes you may need it, and sometimes you may even need, like some variables should be delayed and some shouldn't. And then this system actually also provides that. So for the evaluation, we have 3 evaluation metrics. One for accuracy, we calculate this denominator, which is the marginalized log likelihood. And then the second one is we compare the execution times, because our claim is statically delayed sampling should be faster than dynamically delayed sampling. And then the third one is expressiveness, because we expect dynamically delayed sampling to be able to handle more models than static, because there are like some issues with static in a sense that we are doing that at compile time, so we may not have all the information at compile time. So we evaluate that on 3 models, and first of the models is latent Dirichlet allocation model, and this is a topic modeling. And on the top, we see the marginalized log likelihood, and then we evaluate these the log z with 3 cases, where the left-hand side we have like no delayed, and then the second is we evaluate this with dynamic delayed, and then finally with our static delayed approach. And we expect dynamic and static to give the same accuracy because they are doing the same operation but at different times. So here we got what we expect, in a sense that dynamic and static gives the same results, and then execution times for them, we see that static is better than the dynamic version. And one thing is we see that no delayed sampling, the version where there is no delayed sampling, does not converge because the model is too high dimensional. So, I mean, we have tried this on like a toy data, and with a small data, it converges, but it's impossible for it to converge with such a large, high-dimensional data. So the second result is Bayesian linear. We tried it on Bayesian linear regression. Here it was a smaller model, so we can see all of them converges the same result, but of course, with delayed sampling, it converges much faster, or with less number of particles. And we can see that, again, static execution time is much less compared to the dynamic version. And finally, for vector-borne disease model, this actually shows the limitation of static delay sampling because we are not able to handle recursion. And the main reason for that, it becomes so complicated to encode this at a compile time. And then for this, dynamic delay sampling, of course, performs better than no delay sampling, but this is just a showcase that in some cases you may need dynamic delay sampling rather than the static one, but if static one can handle it, then it is better to use it. So the conclusion is we presented a compile time approach for delayed sampling algorithm, and then we implemented this approach in the dynamic version in a statically typed probabilistic programming language, and you can find the paper there. Also, we have a GitHub repo where you can find always the up-to-date version of these implementations. Thank you for listening.
Thank you very much for the presentation. Do we have any question in the room?
Yeah, thank you for the interesting talk. The idea of delaying and essentially forcing the delayment reminded me a lot about tongues and creating tongues in, for example, OCaml and then forcing them. Have you thought about going the Haskell way and make any of all samplings delayed and force them automatically?
That's a good question. I think one problem with that is then if we make everything delayed, then it is less efficient. I mean, then it might like include all the cases, but we then make things less efficient. Yeah.
And
Yeah.
But so you move some processing that you did initially at runtime to compile time.
Yeah.
And it's saving some time, some execution time at runtime.
Yes.
And what I didn't see is what is the overhead at compile time now? I mean, is it taking a lot of time? Because we also expect when we compile that it's super quick in some way. So
Yeah.
is there some impact?
Yes, there is an impact on the compilation time, and then I think most of the cases that is negligible, but in sometimes if the model is too high dimensional, then it might actually, because we kind of see it here. No, sorry. Yeah, I don't have the result for that, but like if there is like a high dimensionality, then while handling the plates especially, we might introduce some compile time overhead.
Just for the sake of my curiosity, what is the order of magnitude? Milliseconds, minutes?
Seconds?
Okay.
Seconds?
Thank you very much.
Thank you.
Okay, so I think we can thank the speaker again. Thank you very much.
Thank you.